So hi, I'm Theresa, and I'm going to start with this presentation, and then later on Esther is going to continue it. The people who know our presentations from the previous IMCs know that we usually show very nice videos and images, but I think this was all covered in some presentations before, and we are doing a more theoretical one this time. So let's see how this works out. So we're going to talk about the luminous efficiency and the difficulty with its determination. So just short as a motivation, the luminous efficiency, tau as we will call it later on, is used to determine the mass of an entering object, of the meteoroid, from optical data. It's of course a very important factor, you all know it, but still it's quite poorly understood. There are still some difficulties with that. We found this nice image in a publication that compares a lot of different publications, showing that the luminous efficiency that is assumed and used varies by orders of magnitude. So it's still, there's a large discrepancy between that. We also had a look at different publications and took a lot of different values, and we found that the luminosity varies between 0.02 to 40%. After that, and we looked at this mass range of 10 to the power of -6 to 10 to the power of 13 kilograms. So there's a really big shift between the luminous efficiencies that are assumed. So how do we find the right luminous efficiency? Well, it's usually used to calculate the meteoroid mass. So we thought, how about we look at it from a different angle, from just from behind. So we used data where we could determine the meteoroid mass very well, and then see what would the luminous efficiency be. So here you see some data from the Frippon network, where we have very nice velocity and height information in meteoroids. And with this we can use a least square fit to this data and calculate to the deceleration data and calculate the entry mass of an object. With this we can determine two different dimensionless parameters. One is the shape change coefficient mu, which just gives us an idea of how the shape is changing while the meteor makes its way through the atmosphere. This is between 0 and 2/3. And the luminous efficiency, of course, tau, which is just the mass loss to luminosity rate of this meteoroid through the atmosphere, which is given in 0 to 100%. So here you can see one nice firewall that we had a look at. This is intensity over the relative velocity. So at the very left, it's the highest velocity where it starts entering the atmosphere. And we found a mu of 0.68, which is higher than the threshold, but still in the error margin, and tau of 1.5% for this one. Yeah, we find this mu and tau when we fit a least square method to this intensity data, to this light curve, and then just take the optimal parameters mu and tau for this. If we have a look at how the light curve changes with different luminosity efficiencies and mu's, we see that only the height of the peak is influenced by the luminous efficiency, and the shape of it and where the peak is influenced by the shape change coefficient. And yeah, what we had to look at for the intensities is, of course, the magnitude of the fireball, which changes, of course, during its way through the atmosphere. Here you can see one example, which is the one that we showed before. And we had a look at the magnitudes of the different stations that recorded this fireball. And then we tried to exclude all the light curves that show faulty data and also the points that were not so correct. But we still think that this can be really uncertain, so this is something we have to keep in mind for the determination of the luminous efficiency.
Okay, now I just will show you some of our preliminary results. So everything is still preliminary. We are still working on refining and making the method some better and exclude some uncertainties as good as possible. So we analyzed 294 Frippon events. So all of them were detected by at least 2 of these Frippon cameras. And here you see the event count of these events over the luminous efficiency we found for these events. So as you can see, there's a large difference between the values we found. So we span a huge range and over orders of magnitude, and even we have values around 100%, and this is not very physically possible, we think. So we are still looking for uncertainties. Yeah, we had a look at tau in literature, and this is just one example of work who found, they analyzed quite small objects, and they found a dependency on the luminous efficiency on the mass. And since most works in literature most say that the luminous efficiency depends most on the velocity, we also investigated this much more. And here are our preliminary results for the luminous efficiency in percent over the masses we found for the objects. You see the blue and the orange curve, which are some literature results. So, perfect, thanks. And you see the other two lines, which are some fits we applied through our data points. As you can see, we also see a dependency, and we have a similar slope. All of these works have similar slope, but shifted fits. So maybe there's an instrumental bias we see. So our results are much larger than the others. And then we had a look at possible uncertainties, and our luminosity depends on, amongst others, sure, on the luminous efficiency, the shape change coefficient, and the entry mass of the object. And luminosity is proportional to tau and ME. So we thought about the largest uncertainties we could imagine, and the mass depends on some measurements, which we think are quite certain. One of those is alpha, which is the ballistic coefficient, and computed from the high information and velocity information. And we use this value as computed by the three-prong pipeline. And the entry mass depends on, is proportional to alpha to the power of -3. So this would affect the results a lot if there are uncertainties in alpha. And then we have some assumptions. Sure, the most important parameter we think is the meteorite bark density. And because values in literature vary a lot, and the mass depends on the density to the power of 2. So here we have a closer look at the moment. So to give a brief outlook, we are still working on a validation of the model, and to make it better, we would like to have a closer look for the analysis of light curves, because at the moment we do not take fragmentation into account. But as you can see in this very nice example for fragmenting fireball, we have fragmentation in most of the cases. And our fireballs are in most cases, because they are detected with all sky cameras, quite large. Yeah, and we would like to define more uncertainties, find them, and maybe we can exclude some of them. Yeah, to give some our references and to end with a nice video, just that we also have one in our presentation. And it's an emotion, so thank you for your attention.
Thank you. Thank you very much. Someone started something to stay. Circo raised hand. Circo.
Hey, Theresa, Esther, you said that your mass range is terminated by 10 to the 13 kilograms. So can you tell me what is your sample there for a billion tons?
These are the literature values we had a look at.
Okay, so that can be hardly any meteors, fireballs, whatever.
Yeah, we had just a comparison of the literature values that were there, and this was the size range that they were looking at.
We have about 10 to the -5 till 10 to 2 to the power of 2.
Like that, yeah.
The large ones are from Nemchinov and Svetsov. I mean, these are models, and they calibrate them with the Chelyabinsk event. So they look at 20-meter-sized objects.
Okay, thanks.
No problem. Anything else?
Anyone with further comments, questions? Apparently, the slide curve analysis is not an easy thing.
Yeah, not so many nice images. We were really sad.
Yeah.
So that's one of the reasons.
Yeah, like,
Yeah.
right.
Analyzing variable star light curves is essentially much simpler, at least in terms of how to analyze. So if there is no one else, I try to encourage people. Yep, someone.
Yes, Felix.
Yeah, Felix.
So, yeah, so the mass computation I only base on deceleration normally, because that is much more straightforward. Could you say something about the comparison between the two? Is there are there differences, or are they similar, the outcomes?
We didn't have, we did it the other way around. So we used the mass that was computed from the deceleration data and then tried to find the luminous efficiency with it. So it would, be a circle if we now applied this luminous efficiency again to the luminosity data.
Yeah, oh yeah. Yeah,
Okay.
clear.
No problem.
All right, thank you. Looking at the timetable, still. But if there is no other question, let's thank Esther and Teresa for their very nice talk. Thank you.